In this lesson, we're going to look at derivatives of inverse functions. First, let's begin with a little bit of a review of inverse functions. Notation that we use: if f is a function of x, then f to the negative 1 power of x. That's called the inverse of f. And we generally don't read it as f to the negative 1 power, we just read it as f inverse of x. The idea behind an inverse is the inverse function is the reverse operation of a function f, which maps values in the range back to its domain. So, for instance, if I have a function f which has some domain, I have 5 values here, -2 to +2, and some range values. So I'm going to map -2 to -4, -1 to -2, 0 to 0, 1 to 2, and 2 to 4. So this mapping tells me how to get from one point in my domain to the output value in the range. If I had an inverse function of f, what I want to do is go back. So if I put -4 into my inverse function, what I want is to be able to get -2 back out. If I put -2 into my inverse, I want to get -1 back out, and so forth. So I essentially want to swap my domain and range, and that's how an inverse will work. The existence of an inverse: these functions only exist for values in the domain of f which have unique values in the range. So what we say is the function must be 1-to-1 on its domain. The way that I've drawn f and f inverse here, these functions would be 1-to-1. But let's say, for instance, I have the value 3. And 3 is an input value to f, but for some reason 4 is also an output value. Well, the problem is, when I input 4 into the inverse, do I return the value 2 or do I return the value 3? It's questionable at that point. So the inverse is not actually a function at that point. So you have to have this property of the original function being 1-to-1. So here's an example that shows the necessity of a 1-to-1 relationship. I have the function x² + 2 drawn for you, and some point p that I can move around on this curve. If I'm going to find the inverse of this function, you basically are taking your x and your y values and you're swapping them. And so you get a reflected point on the opposite side of this line. Alright, so wherever p moves to, q follows in suit, and it's just the same x and y values, but just flipped. So we just swap the x and y is all we do. Now, if I take all of the points q and try and make a function out of it, then what happens is, on this side, all those points q are just fine. When I cross this vertex point, I now end up with a problem. This is no longer a function. So this would no longer pass a vertical line test. If I drew a vertical line on this graph, it crosses the graph at 2 separate points, which means it's not a function. So in order for an inverse function to exist, you have to have the property of being 1-to-1. And the reason that this function is not 1-to-1 is because it fails the horizontal line test. And to fail the horizontal line test, if you draw any horizontal line and it crosses the graph at more than one point, it fails that test. So what we need is in order for an inverse to exist, we need both a horizontal and a vertical line test to pass. Now, supposing that we have a function that does pass a horizontal and vertical line test. For instance, a line. A line is definitely going to pass both of those. And you can draw out a sketch of a line and prove to yourself that that would be the case. But once you know that your function is one-to-one, then an inverse function exists. So if you want to then calculate what the inverse function is, you swap the x and the y value in the equation and then resolve for y. So if I'm looking for my inverse function, then I could swap my x and my y and say x equals 3 times y plus 4. So literally just switching the position of these two. And resolve for y. So if I subtract 4 from both sides, that gives me, come over here, x minus 4 equals 3y. Or if I divide both sides by 3, I have 1/3 x minus 4/3 as the new function y, but that is my inverse function. So my inverse of f is 1/3 x minus 4/3. And that's how you calculate an inverse function for any one-to-one function. Now, there are some different properties of inverse functions that we want to take a look at. First of which is if you compose an inverse function with the original function, you end up with just the value x. Essentially what this is saying is whenever you put a value x into a function and get a result out, you take that result, put it back into your inverse, you get right back to where you started. You can see this property up at these bubble charts. So for instance, if I take -1 and put that into my function, the output for -1 is -2. Then if I put -1 into my if I put -2, which is the output, into f inverse, the output of that is -1. So the result of composing these two, of doing f evaluated at f inverse of -1, just results right back to -1. The graph of f and f inverse are symmetric about the line y equals x. I already showed you that in the app. It just, when you're swapping your x and your y values, you're basically creating that symmetry about that line. Next is that the slopes of the tangent lines of f and f inverse are reciprocals. So what that means is the derivative of f of x is equal to 1 over the derivative of f inverse. So let me show you how this last property works. I have the graph of the square root of x minus 4 and the line y equals x, which we know that the points P all reflect over to Q and draw that mapping of a new function. I'm not going to trace it out, I'm just going to actually show you what that inverse function looks like. So that is the green function there. So all the points reflected to the other side map on this line, or on this curve. Now, the next thing is we're looking at tangent lines. So if I showed you the tangent line at point P, that shows up here in orange. And you can see the different values of the tangent line over here. It's right now about 1/3 at the point that I've chosen. If we invert that, that's going to give us the tangent at Q. It's what that property is telling us. So if I do the inversion at this particular point, 1 over 1/3 is pretty close to 3. So if you look at the slope at point Q now, it's about 3. So every point along this original function, if you find its derivative and take the inverse, then that gives you the same slope at point P. Because the inverses are always, or the derivatives are always inverses of one another. So you can kind of see that visually here with the different slopes of the lines, but you can absolutely see it over here with the calculation. So this is the slope at point P. Next I have the slope at point Q, and this is actually taking a computation of 1 divided by the slope at point Q, and you can see that it's always equal to the slope at point P. Now let's establish the derivative of some important inverse functions that we need to work with. In this case, that's going to be the inverse trig functions. So things like arcsine, arctangent, and so forth. The proofs of these, I'm going to use implicit differentiation. You can actually establish them using the inverse derivative properties. I just think the implicit differentiation is a little bit cleaner. So let's start with the arctangent of x. So what I want is to figure out what the derivative of the arctangent of x is. The way that I incorporate implicit differentiation is to say, okay, if y is equal to the arctangent of x, then what I can also say is x is equal to the tangent of y. That's how these inverse functions work. So the arctangent of x is the same thing as the tangent of y. Either way, y is an angle measure. So you may have to recall back to your trigonometry, but the idea is when you're using the inverse trig functions, the arctangent for instance, you give it a ratio of sides of a triangle and it tells you the corresponding angle measure. And if you take an angle measure and put it into tangent, it tells you the relationship between the ratio of sides of the triangle. So y, the value y in this case, is an angle measure. And that's really important because if it's an angle measure based off of a right triangle, we can derive some important information from that. So if I call this angle right here in this right triangle y, one thing that I know is that the tangent of that value is equal to x. If you go back to SOHCAHTOA, the tangent is the opposite side compared to the adjacent side. And I've picked x and 1 because if you take x and divide it by 1, you get x. So this is a setup where the tangent of y would be equal to x. So that's equivalent to what our statement says. Now, this remaining side, I'm going to call it b for right now. We can solve for it because we know the Pythagorean theorem says that the sum of the squares of the two shorter sides of the triangle is equal to the square of the hypotenuse. So the hypotenuse then, in this case, is going to be the square root of x squared plus 1. So I can actually replace this value b with the square root of x squared plus 1. So I now know all three sides of this triangle. We'll use that in a moment. Let's take a look at working out a derivative at this point. Alright, so I'm going to try and differentiate this function. So remember here, the way I've evaluated or set up the relationship between y equals arctangent of x and x equals tangent of y, this is the same function because I'm using inverses here. Now, what I want to do is differentiate this statement. One way of doing that, through implicit differentiation, is to just take the derivative with respect to x of both sides of the equation. Now, the derivative with respect to x of x is just 1, but the derivative with respect to x of the tangent of y, that's when things get a little bit tricky. So y, we assume, is a function of x. Okay? Now, if that's the case, I can go ahead and differentiate the tangent of y as I would normally. And the derivative of tangent is secant squared. So it would be the secant squared of y. But then we have to multiply by the derivative of the inside part to complete the chain rule in terms of implicit differentiation. Now, if I divide both sides by secant squared of y, I will get dy dx by itself, because this will cancel out. And 1 over secant squared, if you will recall from some basic trigonometric identities, 1 over secant is how we define cosine. So this is actually the same thing as cosine squared y. So it looks like my derivative would be the cosine squared of y, which is true, but because we have this triangle, we can actually do a little bit better. So, for instance, I can say that dy dx, if it's equal to the cosine squared of y, well, cosine, according to SOHCAHTOA, is the adjacent over the hypotenuse. The adjacent side of this triangle that's adjacent to the variable y, or the angle measure y, is 1, and the hypotenuse length is the square root of x squared plus 1. So that's cosine of y, but the derivative is that thing squared. And if I square this fraction, I get 1 over x squared plus 1. So what we can say here through all of this is that the derivative with respect to x of the arctangent of x is equal to 1 over 1 plus x squared. Now, you can establish the other rules in the same fashion. I'm not going to do each one of them for you, but it's pretty much the same situation. The only thing that differs is when you do an arcsecant. The arcsecant involves an absolute value factor, but that's only there because you need the arcsecant is always an increasing function, so you need the derivative to always be positive. So let me give you the results of all these. So the derivative of arcsine, and I've written this in terms of the chain rule, so the derivative of arcsine u is u prime over the square root of 1 minus u squared. You can see the same sort of form that we had with the arctangent. It just simply is setting up that triangle. You're setting up two different sides besides, instead of the opposite side and the adjacent, with the sine, it's the opposite and the hypotenuse. And that's where you get the square root of 1 minus u squared in the end. For secant, if you do the arcsecant, what you end up with is u prime over the absolute value of u times the square root of u squared minus 1. And arctangent, as we just saw, that's what this looks like. But with arctangent, I've written this in terms of a function u of x. So instead of it just being 1 over 1 plus x squared, it's u prime over 1 plus u squared. So this is the formula that you should make sure you know. The remaining trig functions, are cofunctions, that is. They're basically the same. So the arccosine is pretty much identical to the arcsine derivative. It's just negative. Same thing for the relationship between arcsecant and arccosecant. Same relationship, same function in the end, but negative. And likewise for the arc cotangent. So the basis functions are sine, secant, and tangent. The cofunctions are cosine, cosecant, and cotangent. And one thing that is still pretty nice is anything involving a cofunction in derivatives is resulting in a negative derivative. So memorize the first three and then learn that the last three are just negatives of those. Let's take a look at an example. Let's find the derivative of the arc sine of 2x. So the derivative of arc sine 2x, we can go through a whole process and set up a triangle, but if you memorize these formulas, you can get these derivatives pretty quickly. So the formula for the derivative with respect to x of the arc sine of some function u is u prime all over the square root of 1 minus u squared. So the function u in this case is the 2x, the argument of the function arc sine. The derivative of that is just 2. So the derivative of the arc sine of 2x is 2 over the square root of 1 minus 2x squared. And just be careful because make this 2 over the square root of 1 minus 4x squared. And you're done. You've got the derivative. You're just basing it on a formula, that's all. You just have to make sure you know the formula. The derivative with respect to x of the arc secant of e to the 2x. Well, in this case, the function u is e to the 2x, and the derivative of that is 2e to the 2x. Now, if I do, and I did not mean for there to be like a dot in between my 2 and my x. I'm going to remove it just to make sure it's clear. In order to do the derivative of arc secant, the derivative for arc secant of some function u prime over the absolute value of u times u squared, the square root of u squared minus 1. So the derivative here, oops, meant to put that in the denominator. So the derivative with respect to x of the arc secant of e to the 2x, u prime we see as 2e to the 2x, and then in the denominator it's the absolute value of u, so the absolute value of e to the 2x times the square root of u squared, so e to the 2x squared minus 1. Now we can simplify this one a little bit. So for instance, I can say that first off, e to the 2x is a positive function. It's whenever you put a value into an exponential function, whether you put a negative number or 0 or a positive number, the result is always positive, so the absolute value isn't necessary. So you can just take away the absolute value. And then when you take the e to the 2x and square it, when you have something raised to an exponent and then you're raising it to another exponent, you can simplify by multiplying your exponents. So 2x times 2 would be 4x. So this would be e to the 4x minus 1. And lastly, if you'll notice, I have a factor of e to the 2x in the numerator and denominator, which can cancel out. So this should become 2 over the square root of e to the 4x minus 1. Here's another. The derivative with respect to x of the arctangent of 3x. So u is the argument here. U prime is just the derivative of that argument. So the derivative with respect to x of arctangent of some function u is going to be u prime over 1 plus u squared. So in this case, this derivative of the arctangent of 3x would be 3 divided by 1 plus 3x quantity squared. And there's not much you can do to simplify here, but I definitely would recommend multiplying out this 3x quantity squared and make it 1 plus 9x squared.